Sir, please begin.
Okay, thank you
Okay,
so much.
okay,
Okay,
sure. Oh,
first of okay, so good morning to all of you. First of all, I would like to introduce our today's speaker and guest, Dr. Purvesh K. Nanavati sir. Purvesh sir is working as an assistant professor in Metallurgy Department, Government Engineering College, Gandhinagar since 2010. Sir is BE in Production Engineering, ME Metallurgical and Material Engineering in ME in Metallurgical Material Engineering, PhD in Metallurgical and Material Engineering. Sir has also Diploma in International Welding Technologies from International Institute of Welding. Sir is author of many technical blogs, as well as Sir has a 15 years of teaching experience in mechanical and metallurgy at degree diploma, self-finance and granted government institute since 2005. Sir is also contributing as an assistant visiting professor for technique teaching welding metallurgical course in L&T Courses ME in Welding Technology program running in MS University Baroda since 2018. Sir has been part of many technical talks as well as many webinars organized around the state as well as in the nation. Sir also works as a project engineer in EDII Engineering Cluster Development Project funded by World Bank, SIBDI and NABARD. Many publications is under Sir. So, Dr. Purve sir, it is very, rather than warm, I would like to full welcome for you as winter summer is going on. So, sir, we are very happy to have you as a today's speaker. And, sir, we are welcoming you again behalf of all the automobile department of Parole University. Sir, you are online.
okay. Thank you very much, Professor Yes, sir, for this very nice introduction. And I'm very much happy to be here. And I welcome you all students of Automobile Engineering Department, Power University, Baroda, uh, for this talk. And I'm very much thankful to the head of department, Professor Shailesh Parmar sir, and Professor Yes sir, for considering me for this invited talk. Well,
Thank you, sir. It's our
I
privilege,
think,
sir. Our privilege.
sure, thank you very much, sir. Thank you. Fine. So I'm now going with my slideshow. Fine. So these are the contents I'll go through. So I will start with the engineering metals and their alloys introduction. Then we'll see some classification of alloys at a glance. Then welding behavior, known as weldability, and weldability is issue specific to metals and alloys. Then we'll end up with the references. So this is the flow of my presentation, and I believe that at the end of presentations, at least you students will definitely develop some interest in weldability, the welding behavior. You get to know about the behavior of metals, different metals and alloy towards welding processes, and you will come to know about some specific issues and their troubleshooting approaches. So with this, I'm going to start. So in these pictures, you are seeing many constructions. Constructions belong to power industries like boilers, pressure vessels, heat exchangers, and wind energy, and automobile, aircraft, shipbuilding. So the metals are used everywhere, right? So metals and the welding process, right? Metals and their manufacturing process, welding is used everywhere in all sectors. So that is why it is very important to know about the various types of metals they are meeting this requirement, and the welding behavior of the metals that can uh, be useful for construction of these designs in various sectors. So materials of constructions are generally mild steel or high strength low alloy steels in various sectors like infrastructure, automobile, shipbuildings, and high tensile steels in defense and hydel plants, and creep resisting steels. They are also demand with manufacturing of boiler and piping in power plants, and stainless steels. They are used with the chemical and petrochemical plants, refinery, cryogenic, food processing, and pharmaceutical industries. And aluminum, because of its lightweight, its benefit of structural, light structural constructions works, dairy equipments, and in bus bar, electrical application. Then we have a some non-ferrous metals like copper, nickel, aluminum, and titanium. They have finds application with the uh, in the in the food industry, in the chemical, and in the uh, power generating equipments. So there are various materials of constructions used abundantly. Now, regarding the classification of ferrous alloys, there is a partition between the cast iron and steel, because cast iron can only be cast, right? They cannot be uh, given a shape because of their poor ductility. So that is decided by the percentage of carbon present in a composition. So high carbon and alloy carbon have carbon percentage more than 2%. There are cast iron. There are a variety of cast irons like gray cast iron, white cast iron, malleable cast iron, ductile iron, high silicon cast iron, and whatnot. And the steels have carbon percentage less than 2, so practically 1.6, and they are ranging from 0.03 to 1.6. The steels have again categorized or subclassified into plain carbon steel, low alloy steel, high alloy steels, right? So uh, I hope you students of automobile engineering are studying various because you have to deal with the engine components. So there are various parts like cylinder liners, like cylinder head. They are made of cast irons, right? And steels. The alloy steels are used for the shafts, for the connecting rod, crankshaft, bushes, then engine valves, and many more application. So, and some of the materials you are also studying as a part of your curriculum. But this plain carbon steel, low alloy steel, and high alloy steels, these are the main focus of our today's talk. We'll also touch upon some non-ferrous alloys as well. But this plain carbon steel is again subclassified into low carbon steel, medium carbon steel, and high carbon steel based on their percentage of carbon, less than zero point 0.2, between zero point 0.2 to zero point 0.5 and zero point 0.5 respectively. And low alloy steels where the total alloying elements percentage are less than 8, and there are generally chromium molybdenum steels, chrome moly steels, popularly known as in the high temperature applications. And the high alloy steels have alloying elements less than 9%, but their chromium is presented more than 9%. So you use for high temperature applications and corrosion resistance and wear resistance. So stainless properties achieved by means of chromium, because chromium forms Cr2O3, passive oxide film on its surface, so that takes care of the corrosion resistance. So these are the classification of ferrous alloy. Again, the classification could also be based on the various aspects, like based on the composition, based on the manufacturing methods, how the steel is being manufactured, right? In the steel making route. Then there are finishing methods. There are deoxidation practices in steel making, refining methods. There are microstructures obtained, then required strength, and their heat treatment undergone. So these are classification is also based on the different aspects as given this table. Now, uh, talking about the plain carbon steel. So you please see on the cursor where my cursor is hovering, the plain carbon steel, when the carbon steel has been subsequently alloyed with chromium, molybdenum, and niobium, vanadium, nitrogen, their properties are improved. Properties like high temperature strength, pitting corrosion resistance, creep corrosion resistance, then high temperature uh, strength. So they have been also microalloyed with some alloying elements like vanadium, tungsten, boron, and titanium. So on the top left, you would see a picture of a steam pipe, which could be used for 600 degrees Celsius and pressure around 30 megapascal exists, right? So this kind of power pipe or steam pipe, you know, um, what is the idea of showing this picture? Because with the use of various grades, if you manufacture this pipe with for this application with say P22 material, then their thickness is going to be around say 150 millimeter. But the same for the same parameters, if the pipe is designed, then their thickness could be around say 77 meters. So some reduction in thickness with X20 materials. X20 materials we can spot somewhere here, right? This is X20 material with the addition of carbon, chromium, and tungsten and vanadium. But if the same can be produced with a P91 material to meet this uh, application, service uh, temperature and pressure, it could be used with only a 2 inch, say only say 50 mm, right? So you could understand the role of alloying elements, right? So this chromium and molybdenum and tungsten and some micro alloying elements can reduce the thickness required for a different grade of chromoly steel. And chromoly steels are extensively used for elevated temperature applications and where the creep resistance and steps stress rupture properties are required. So by this slide, I wanted to give you idea about the role of alloying elements, right? Now, talking about the stainless steel families. Stainless steel families have 5 members. Austenitic stainless steels. They have the popular grade is 18A. The grade is 304, where 16% chromium and 6% nickel. Ferritic stainless steel is having a 10.5 to 18 percentage of chromium, and the commercial grade is 430 and 409. Duplex stainless steel, they are having a mixture of ferrite and austenite. There are two-phase steel, and the popular commercial grade is 2205 and 2304. Martensitic stainless steel. Martensitic stainless steel is having a high percentage of chromium, 12% chromium, and commercial grade are 410, 416, and they are of ferritic type because chromium is a ferrite stabilizer. And last category is pH steel. There is no precipitation hardenable steel. They contain chromium and nickel, but they having a very good tensile strength. And popular grade is 70-4 pH. So 70 is stand for chromium percentage, 4 is for nickel percentage. And the strength can be obtained by the precipitation hardenable treatment. But these austenitic stainless steels are not hardenable. They can be annealed only. Ferritic stainless steels, they cannot be hardened for the room temperature. The structure is ferritic. Duplex stainless steel, they are not hardenable. Only martensitic stainless steels can be hardenable, and the precipitation stainless steel hardness strength mechanism is different. It is not the same as, but it is undergoing a solution and aging treatment. So these are the family of stainless steels. They are used for different application. Now, moving forward for austenitic stainless steel family. So again, austenitic stainless steel family, their popular grade are 304, 316, 316L, 316N. Again, we need to understand the role of alloying elements like, you know, this chromium, this nitrogen, or some niobium, and so there are again grade like 321 where the titanium is added, 347 where the niobium is added, just to meet the requirement. Because when we have to put these steels to uh, environment where there is a chromium carbide or some sensitization issues are there, right? So we use 321 grade, 347 grade. So there are very specific applications and to this stainless steel family. Overall, austenitic stainless steels are good corrosion resistance and they are suitable for high temperature. But the drawback is they are susceptible to chloride stress corrosion cracking. So with chloride environment, with the saline environment, they suffer from stress corrosion cracking issues and pitting corrosion issues, and they are not good for higher oxidation, not for the high temperature application more than 350 degrees Celsius, because they are to oxide scaling, prone to oxide scaling. Next is a ferritic stainless steel. Ferritic stainless steels can they are very good corrosion resistance material. Popular, grade is 409 and 430. Again, they are not suitable for a high temperature. They are subjected to 475 embrittlement. So European country people call it as 885 degree Fahrenheit embrittlement. So what is 475 embrittlement? Because when these ferritic steels are exposed to 475 degrees Celsius during service for a longer period of time, the ferrite decomposed into some brittle phases like sigma and xi phases. So the structure becomes brittle and the structure is no more able to take the stresses and the failure of structure takes place. So they are not suitable more than 475 degrees Celsius. Martensitic stainless steel. Martensitic stainless steels again they are magnetic in nature, but the nickel is not present. Here, chromium is the main alloying elements, but this steel is hard to weld. This steel, martensitic stainless steels are used for corrosion resistance application. They are very good hardenability. They are hardenable by heat treatment, but they are not easy to weld. They are hard to weld because hardness or hardenability and weldability are they are opposite to each other. Higher the hardenability, poor the weldability, and vice versa, right? Now next is the duplex stainless steel family. With duplex stainless steel family, it is a two-phase stainless steel with ferrite and austenite present, and these duplex stainless steels are used for the applications demanding in a source service application in digester, paper industries, and uh, many applications where the corrosion resistance is required, high pitting resistance is required in chlorine environment, and but they are again not suitable for high temperature applications because they are again subjected to 475 embrittlement, right? Like ferrite stainless steel, because ferrite is also present. So the rod duplex stainless steel structure contains approximately 50 to 55 percentage of ferrite and 45 to 55 percentage of austenite. So the two-phase structure, and the main alloying element here is the chromium, nickel, molybdenum. They are used with the oil and refinery industries. Now, next is about the nickel alloys. These nickel alloys, if you can take a look at the nickel 200 here on the right hand side where I am hovering my cursor. Now this nickel alloy, when these added with some chromium, they will have a high temperature strength. Again, with molybdenum chromium, they will have a very good corrosion resistance, very much resistance to chloride and high temperature environment. So this alloy 625 known as Inconel, C27 known as Hastelloy. They are being used for many applications demanding high temperature. So the noteworthy point with the nickel-based alloy are that nickel-based alloys can be used for the high temperature, they can be used for the low temperature application or for the cryogenic applications also. So again, the role of alloying element is there. The addition of chromium, addition of molybdenum, and addition of copper, and some micro alloying element in a alloys X750. They are giving birth to super alloys. The super alloys are extensively used for the gas turbines requirement. So there is a role of alloying elements in a certain quantity, and the base metal, when this alloyed with various kind of alloying element, they are becoming superior in strength, in mechanical strength, in a corrosion resistance, so they can meet the demand, they can meet with the applications required, right? And again, this on the top of this picture or the slide, you will see a stainless steel with added Fe. So what is the basic difference between the stainless steel and nickel alloys? Can some student knows basic difference between the stainless steels and nickel based alloys? Any students can. Okay, anyway, I think we can have a good introduction after this webinar is over. But there are the but in a nutshell, I wanted to say that the composition of stainless steel and nickel alloys are overlapping. It means in terms of say nickel, chromium, but in a nickel-based alloy, the majority of nickel is there. But in a stainless steel, there is a added Fe, means more iron content is there. So both stainless steel and nickel-based alloys are used for common applications, but specific to the when the application demanding high temperature strength or application demanding the cryogenic strength, right? Or a strength maintained at the cryogenic temperature, nickel-based alloys are most selected, right? So moving to next slide. Now, before I start with the welding behavior, I think it's a good to give you a background of the the relationship between the composition, microstructure, and mechanical properties. So this my presentation is context with the weldability and the metals and alloys and their welding behavior, because in for your automobile applications, most of the time you go for the spot welding, you use GMAW welding, right? So there are many like thousands are spot weldings are there. There are many gas metal arc welding processes are used, and uh, so whenever the metals or any engineering material is the way we describe, right? These different, particularly this low alloy steel and stainless steel. So their chemical composition and thermal cycle. Thermal cycle means during welding, the heat is given to material for uh, obtaining the proper fusion. That fusion can be achieved with filler metal or without filler metal, but this heating and cooling cycle, it is known as thermal cycle, because when the heat is applied through the arc, the temperature rises. At the same time, when the weld joint is or completed, again weld cools, so temperature drops. So this thermal cycle and the chemical composition controls the microstructure, or in other term, put it in other term, microstructure is sensitive to chemical composition and thermal cycle, but the mechanical properties are sensitive to the microstructure. It means microstructure can change the mechanical properties. So it is the microstructure that has to be controlled, right, throughout the uh, manufacturing processes, so you can achieve the end property requirement. So this slide is again giving a idea about the various metallurgical phenomena involved in a process of welding. So in a right top, you would see a picture in a picture you see a heat source is moving. There are two plates. The two plates are going to be joined by means of welding process, and the heat source is moving from this uh, left to right in the direction of this arrow. Now this fusion zone fusion zone, adjacent to the fusion zone, there is a heat affected zone. This zone has been affected by the heat or by the thermal cycle, right? And this weld pool, when the weld pool is passing through this, or it progressing, the weld is progressing at the same time, the molten pool left behind this is going to cool quickly. So in a matter of few seconds, their microstructure is decided, and there are various metallurgical phenomena are involved, like melting and solidification. Because here the base metal is partially melted, you are adding a filler metal, so there will be melting phenomena, there will be solidification phenomena, there will be nucleation growth, because the moment the metal cools, the nucleation will start, and the growth of the grain starts. Then there will be phase transformation. It means initial the structures, when heated, all structures uh, converts to a austenite phase. Then from the austenite phase, I'm talking about various carbon steel, low alloy steel, and they are now transferred back to the ferrite, perlite, and all this, and some cementite, and probably benite. So the nucleation growth, there are many such things are taking place. Then segregation and diffusion, because there are many such alloying elements, like low melting point elements, they are going to segregate. Segregate means gathering, some grouping in between, and there will be diffusion of these alloying elements. There will be precipitation of new precipitates. It means some alloying elements may be precipitated out. Some intermetallic phases may be precipitated. They are not actually, uh, 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 part of this composition, but when this composition of this filler and the base metal mixes together, some intermetallic phases are produced. So their precipitation, some recrystallization and grain growth, the new old crystals, new crystals are developed, or at the expense of the uh, old crystals, and grain growth will take place. There may be some embrittlement. We'll see what is embrittlement. There'll be thermal expansion, contraction, and residual stresses. These things are meant because given a heat by arc of the heat source or the welding process, the material expands, and during cooling, material contracts. And because of this expansion and contraction in a localized region, you see, because in a very localized region, this expansion and contraction is taking place. So the during expansion, surrounding at a metal, base metal is in solid form. It is going to uh, resist expansion. At the same time, during cooling, the surrounding base metal resist contraction. So there will be some internal stresses or residual stresses developed in a welded joint, and these are residual stresses are giving problems. We will see what are the problems. So this kind of structure, if it is not cross weld heat treated, right? In automobile structures, like dual phase steel, or the steel like high strength low alloy steel, HSL steel, if they are not given proper treatment, excuse me, so they may be subjected to embrittlement, because many uh, hard phases are present, like martensite, like benite. The martensite has to be tempered by means of post-wear treatment. Likewise, okay. So again, during cooling, the phase transformation is taking place, and the phase transformation, these phases are produced, like martensite, bainite, fine, coarse, pearlite, spheroidites. So this is a continuous cooling transformation diagram. It is a temperature versus time. So, and above it is a transformation, or above is you take total temperature. It means above 723 degrees Celsius approximately. The phase, everything is austenite in state, because I had told you that whenever these it is heated above the are hitting above the welding temperature, the fusion temperature, the phase is developed is a austenite, single phase in a carbon steel low steel, right? And this whenever it cools by different cooling way, the way the the cooling is achieved, they are either from coarse pearlite, fine pearlite, bainite, or if it quickly cools, it forms martensite. So no, it's a matter of few seconds available, and the microstructure is decided. So you can understand this in a welding processes, the welder has a very least control, or so how the over the you know the development of microstructure. So the procedures of the welding procedures has to be decided, has to be checked for producing a production welds, right? Procedures means what kind of consumables will be used, what kind of parameters can be used, like heat input, interpass temperature, what kind of pre and post well heat treatment, what kind of shielding or flux will be provided, or flux coating, or processes will be used depending on the processes. So there are various procedure qualification test, right? Now we are coming back to our main topic. I hope you have now, by this time you know this, that the weldability is all about behavior of metals under welded condition and during service conditions, right? Because under welded condition is different, because some of the defects like hot cracking, they can be immediately cracked after welding. But during service condition, like delayed cracking, like hydrogen embrittlement, that can happen during service. It means once you have a produce a part, you have welded component or a welded assembly, when it is put into the service, and if it is subjected to temperature for prolonged exposure to say some elevated temperature range like 400, 500, and so on, there may be subjected to creep. So during service, they can also fail. So weldability is all about the behavior of metals. So in other terms, it can also defined as a ease with metal can be welded to give the required service, because uh, the metals are selected based on their strength, based on their you know uh, properties like corrosion resistance, based on their resistance to uh, various various environmental factors, right? So, is the amount of nature of the problem you face to weld a material. Weldability, other terms, can also be known as the amount and nature of the problems, because when we are uh, joining the materials by process of welding, we come to know about the issues, right? That study is also known as weldability, and is the ability of any material to weld with other metals in simple terms. But these are the various definitions about welding behavior, or say the weld ability. But there is a standard definition given by the American Welding Society, and the definition is weldability is the most often used to define a material's resistance to cracking during fabrication. And these are the other than definition of so that the good availability is resistance to various forms of cracking during welding, requiring essentially no work or repair. Because if you, during the process of welding, if your part is cracked, then again you have to rework or repair it, right? So now issues with the weldabilities, like in your automobile, when the austenitic stainless steels are used, when the particularly the austenitic stainless steels are used, right? Like in a muffler or in a silencer. Most of the time, it's a low carbon steel coated with a nichrome plating. But some uh, grades of automobiles where the austenitic stainless steel is used, there is a problem in the weld zone is a solidification cracking and a micro fissuring. These are known as micro cracks. On the heat affected zone, I hope now you understand the heat affected zone. It is the area adjacent to the weld line on the other side, or it's the area which has been subjected to affected by the process of heating and cooling, or say the thermal cycle. So where if the hydrogen, if the weld pool is not protected from the atmosphere, and the hydrogen gets diffused into the structure in the heat affected zone, then hydrogen induced cracking, or say cold cracking, can take place. Or liquefaction cracking is another phenomena. It is happening because of the presence of low melting point metals. And reheat cracks particularly taking place with the chrome moly steels and creep resisting steels. And problems, other issues like porosities, with welding of aluminum will end up with a porosity problem, and oxidation of reactive metals like aluminum, chromium, molybdenum. They are very reactive to oxidation. So reduced joint strength, that takes place particularly the welding of aluminum, because if your strength of aluminum drops because of the welding processes, right? And the strength drops also in the heat affected zone. So you know the logic, right? Because you join the material for doing some structure, for obtaining uh, for making assembly, right? Why you are going for welding? You are connecting different members, and you know the load is transferred through the members. Being a mechanical or automobile engineer, when the load is transferred through the members, they are transferred across the welds. You put in a different parts, right? But these parts, if these welds have poor strength, then their base metal strength, then whole stress is going to be concentrated on the weld metal or on the heat affected zone. So the cracks will be developed there. So weld metal and the heat affected zone, or the weld, should have a matching strength with the base metal, right? So then only it can be used uh, satisfactory for the application. Then there are problems like reduced corrosion resistance. Because of some uh, uh, say precipitations, because of some microstructure development, the corrosion resistance will be reduced, and the weld will be subjected to uh, say pitting corrosion or stress corrosion likewise. So in this table, I try to explain the weldability problems. I will sum up the weldability problems with various ferrous and non-ferrous metal. So uh, let us understand first the oxidation of reactive metals. If you weld non-ferrous like aluminum and magnesium and titanium and their alloys, and auto in the automobile industries, from the road transport to the you know say aerospace, or say the aircraft to aerospace application, light metals alloys like aluminum, magnesium, and titanium are used, but their welding is very challenging because this aluminum can quickly form L2O3, aluminum oxide. Magnesium has high reactive oxygen, magnesium oxide, titanium dioxides. So during welding, there has to be a proper shielding. So in a welding of titanium, there will be proper shielding is to be given, say back purging, or say the shielding, or so there are many ways in which the molten weld pool of these materials have to be protected. Then gas metal reactions will also take place because of some poor shielding, or uh, poor welding positions, the nitrogen, oxygen, or hydrogen gases from the atmosphere quickly react with the molten metal. So it give a defect like porosity in steel, in oxides porosity in copper and nickel, and hydrogen porosity in aluminum and titanium. So the filler metal or the welding consumables make use of the deoxidizer. So these oxygens, dissolved oxygen and molten weld pool can be removed with the technology, right? They have been removed. Deoxidizers. The deoxidizers can be aluminum, magnesium, and right? Then vaporization of the low boiling point metals like uh, when the zinc is welded, generally zinc is not welded, it is a brazed process of brazing. It is uh, joined, but the brasses, when the brasses are joined, the zinc having a low boiling point, like 440 degrees Celsius, roughly, right? So there is a different technology known as brazing technology, and the tin bronze filler are used at a lower current. Then hot cracking issue. This is the main issues with austenitic stainless steel, and it is because of the presence of some no melting constituents or impurities like sulfur, phosphorus, or lead present in a hot or in a molten metal. So these low melting points are not freezing at a temperature rest of the metal is freezing, right? They are freezing very last. So what happens? They segregate at the grain boundary, and during cooling, we will see that grain boundary shrinks because of the cooling stresses. So there'll be separation of these grains where the low melting point constituents are present or segregated in the grain boundary. So that results into the cracking. So we have to use a two-phase filler metals for SS stainless steel electrode with 5% of ferrite. I'll come to this. What is the benefit of using the 5% ferrite, or what is the role of ferrite in a where in a welding of stainless steel? Then hot cracking in the heat affected zone. Again, embrittlement issues, liquation in a heat table of aluminum alloys, hot crack, and use of low melting point alloys. I also included some slides on aluminum, welding of aluminum, because it is most used material in your automobile application. But for automobile application, we'll try to use a material with a lower melting point alloys near to eutectic point, or with aluminum silicon or aluminum magnesium. Aluminum for 5% silicon, aluminum 5% magnesium. Why? I'll explain when the slide comes in subsequent slides. Then there'll be cold cracking in the heat affected zone, particularly in carbon, manganese, and low alloy steels. Because of the hydrogen, when the hydrogen diffuse into the welded carbon, manganese, and alloy steel, this hydrogen can crack. And the remedy to this problem is use of preheating, so that the hydrogen can be removed, post-well heat treatment, and low hydrogen consumables. Or using electrodes, they have a very low hydrogen consumables, low hydrogen content, right? This is known as low hydrogen practice. The reduction in heat effective zone strength. So I mentioned you that in welding of some precipitation hardenable aluminum grades, the hardness or the strength drops because of this welding process. So this kind of behavior is because of the highest heat input. So we have to control the heat input, and we have to control the uh, parameters of solution and heat treatment after welding. The reduction in corrosion resistance, like stainless steel, because why stainless steel used? They are used for providing good corrosion resistance. But what have if they are subjected to uh, poor corrosion resistance? Then there is no point of using the stainless steel, right? So the heat affected of the stainless steel welds due to chrome carbide precipitation, and this, if the sensitize, if this uh, grade, sensitized steel is used for the corrosion environment, it it will fail, right? So we have to use the stabilized grade of stainless steel, or extra low carbon grade steel, ELC grade steel. So right, 321 steel, 34 steel, or 0.003 percentage low carbon steel, right? If you read a suffix like 304L, then it's going to be a steel with a very low carbon, 0.03. Otherwise, 304 normal 304 contains 0.08 percentage carbon. Likewise, 304, 316, 316L, and so on. So, because of this welding behavior, because in the previous slide I had mentioned you, I had tried to explain to you the welding behavior of various ferrous and non-ferrous alloys like carbon steel, carbon manganese, or low alloy steel, like stainless steels, uh, from the non-ferrous parts like aluminum, magnesium, titanium, and these alloying elements, they are grouped depending on their weldability, depending on their properties or weldability, breathability, and mechanical properties. And that has been taken care of in the ASME, American Society of Mechanical Engineers, Section 9. So in the field, when you use a uh, automobile welding of many materials for your automobile application, you'll be using a ASME Section 9, the construction code. There are very construction code for pipeline. There is a API, American Petroleum Institute. There are many different code, ISO code like ISO 15608. So these codes have grouped the various materials according to their welding behavior, right? So what is the logic behind this? The logic is because I had mentioned you that welding behavior is different, right? Different materials have different welding behavior. So to qualify uh, any procedure, uh, we can reduce the number of procedure qualification tests, because if you want to say if you want to weld a two component X and Y, sorry, two metals X and Y, but if the same kind of X and same kind of Y metals are grouped together, so you find it easy, right? So that is why this materials grouping is intentionally and very logically done by ASME section 9 code and ISO 15608. So it is given as a P number, right? Parent matter number, and where the impact is test is a requirement, like in a automobile welding structures, impact is a requirement, right? Because a moving vehicle can anytime meet with the accident, meet with the some casualties, so it should be sufficient impact strength. So there are also given a group number. So P number and G number, parent number and group number. These are very important. So for your reference, I have tabulated the various P numbers, not G number, but the G number are generally G number 1 and 2, depending on their impact strength. The steels are covered under ASME Section 9 code, and there is an International Standard Organization code 15608. These are the group in which the steel is there, aluminum. If you want to find out, so what is the purpose of this? So all aluminum and aluminum alloys for 21 to 25, if they are given a P number, then they have a same welding behavior. This is the interpretation of this table. Then you have to find out what are these aluminum alloys that are ranging from 21 to 25 P number. They have a same welding behavior. It means it is uh, easy if you use a 22, same procedure for 24. If you use the same procedure for the 25, but not for the 26 or something. But with ISO, it is 21 to 26. But if you use a 28, say for example, aluminum alloys, their welding behavior will be altogether different. This can be used. So copper and copper alloy likewise 31, 35. Nickel and nickel alloys 41 to 47 under P number. Titanium and titanium alloys 51 to 53. Zirconium and zirconium alloys 61 to 63. And cast iron, they are not covered in ASM section 9, but with the ISO it is covered as a 71 to 76 as a P number, right? So moving next, so there are some pictures of the weldability issues I had mentioned you. You could see a creak of the, you will clearly see the crack. Excuse me, please pay 1 minute time so I can sip a water. So in a heat affected zone, you could literally see this dark region is heat affected zone, right? These two metals are joined, and you could see this heat affected zone. You could clearly see a crack. There's hydrogen cracking. You would see a center line cracking, right? Here, there is a two plate, one and two plate. They are joined together. You will center line cracking. Then there's a lamellar tearing. There's a new word for you, but the laminar tearing is because of presence of non-metallic inclusions. Because during the steel making practice, some inclusions are developed. There are oxide inclusions, nitride inclusions, sulfide inclusions. So whenever these inclusions are present in a rolled steel structure, right, hot rolled structure, and when you perform welding, you will end up with the cracking, and there is a lamellar tearing, right? Now, for carbon steel and low alloy steel, the most important thing is carbon equivalent, CE, for carbon steel and low alloy steel. So with this formula, if you put the value of your composition into this formula, right, you can find out what is the value of your CE, carbon equivalent. If your carbon equivalent is ranging less than 0.35, you need not to go for preheat or post-well treatment. It means there is no danger of hydrogen embrittlement or delayed cracking, or there is no issues related to cold cracking. But if your carbon percentage ranging from carbon equivalent percentage ranging from 0.35 to 0.55, you need to go for preheat. If it is less than 0.55, preheat and post-fill both are mandatory. And if the CE value, carbon equivalent value, is more than 0.5, this steel is more than difficult to weld without cracking. So this is the idea about the carbon equivalent, and GATE gives the measure of the susceptibility to brittleness. And so, higher the CE, lower will be the weldability. That you can find out from these values of the table. So what are the alloying elements that can be accounted for the carbon equivalent calculation? It is a manganese. It is carbon first, then manganese, chrome, moly, and vanadium, then silicon, nickel, and copper. But they are in very least amount. The coefficient chromium, molybdenum, and vanadium, they are high in percentage. Okay. Now moving to next slide. So I will touch upon two category of steel. One from the ferrous category, that is austenitic stainless steel, that is most used with your automobile application. Then next I'll be using, of course, low alloy steel and high strength low alloy steel are also used, but their the welding behavior, again, you have to go for the preheat, post-well heat treatment, controlling the microstructure. This kind of practice is required. And austenitic stainless steel is susceptible to hot cracking and IGC attack, intergranular corrosion attacks, and loss of ductility due to intermetallic phase precipitation and distortion. Distortion means after welding, the dimensions are changed, or the materials, uh, when after welding materials bends or wraps, or the all dimensions are lost. So to understand the weldability or welding methodology of stainless steel, it's a it is with the help of a pseudo binary two-phase diagram of 60 of nickel and chromium. But just to give you an idea about, it is the way in which the alloy is solidified. If it is solidified in the austenitic mode, or austenitic ferrite mode, or primary ferrite and secondary austenite, or fully ferrite, then microstructure is different microstructure is developed. So in a nutshell, what is important from the austenitic steel welding point of view is it should be solidified under AF mode, primary austenite, secondary ferrite. Then it is less susceptible to cracking, hot cracking issue. Then this hot cracking or the solidification cracking, as I mentioned you, in a taking place in the weld metal, and liquefaction cracking take place in the heat affected zone. So to understand the solidification cracking issue, just to explain you that these low melting metals like sulfur, silicon, phosphorus, they tend to segregate at the grain boundary, and during the process of cooling, when the weld cools, the shrinkage takes place. So the shrinkage is going to uh, just pull apart these two grains from the grain boundary, and you have a literally crack is observed. So this is micro cracks. Now this kind of weld solidification cracking, there's a picture 3110 stainless steel weld deposits. So liquefaction cracking is because of the segregation of alloying elements. Now, this is a worth to understand the picture. This is your weld pool. Now you are progressing from the left to right, and the immediately after your weld pool there'll be a liquid because it is still not cooled down, and beyond this is a pasty. It means it has been cooled or is in a semi-solid form. So during when the welding is in progress, the area near to weld pool is under compressive state because of the heating, the surrounding base metal is compressed because of the expansion. But during when this weld is progress far away from this zone or beyond this or near in the pasty zone in the semi solid or in the under cooling condition, because of the cooling, contraction stresses are developed and the tensile stresses are produced. And because of the tensile stresses, this figure, right? Because of the tensile stresses, the cracks are produced whenever there is a presence of low melting point eutectics in the grain boundary. So they are not going to support the strength, but they are going to separate the grains from each other at the grain boundary, right? At the interface. So you will end up with the process of cracking. Now, it is very important to mention here about the significance of delta ferrite, but keeping with the pace of with time, I just jumping to the main slide or the conclusion side that when you are performing welding of austenitic stainless steel, you have to have a 3 to 8% of delta ferrite present in a structure. Then you can get rid or you can avoid weld solidification cracking issues. So it is a minimum ferrite requirement with your weld metal of austenitic stainless steel depending on the grade, different grade. So for a higher grade like 347, you require 6% of minimum ferrite number. Otherwise for the 316, 1.5 or practically 3 is more recommended. Now for you have estimated your weldability using the carbon equivalent formula, right? I hope you remembered it. CE formula, right? We have seen CE formula, carbon equivalent formula in our previous slide. It is applicable to only carbon steel and low alloy steel. Likewise, for the stainless steels, there are various diagrams, constitutions diagram like Schaeffler, DeLong, and the latest one is the WRC, Welding Research Council constitution diagram, right? And the latest version is a 1992 diagram. So what is the use of the diagram? You put the composition of your base metal, you put the composition of your filler metal, and you spot where you are. If your ferrite number is between the 3 to 8, I mentioned you with the previous slide, right? Then you are safe. It means your weld is not going to crack. This is use of this constitution diagram. The last topic, it is a weldability of aluminum alloys. So welding of aluminum is most of the time done with the gas shielding processes, because with a flux-based processes like SMAW electrode, the process is not successful because the flux use, although the flux use fluoride flux is effective, but it is highly corrosive. So it is not recommended, and most of the time GTAW and GMAW welding processes are used for your aluminum weld structure in automobile engineering. And also some solid state welding processes or pressure welding processes, right? Like friction welding, friction stir welding, and likewise. So I'm telling about the weldability issues in a arc welding processes, particularly in GTW and GMAW. So there are issues like hot cracking, poor joint efficiency, and softening in the heat affected zone. I had mentioned you, like drop in the mechanical strength, resulting in the poor uh, strength and hot cracking issues. So what is the remedy to it? Remedy to avoid the solidification cracking is the use of selecting a filler metal composition, because when you are joining aluminum, you have to select a filler metal for your GTAW and GMAW welding processes very precisely. Secondly, your joint design is also important. Third is your heat input control, and fourth is the grain structure control. So in a nutshell, I tell you these are the various the diagrams giving idea about the cracking versus various alloying element like silicon, percentage silicon, cracking versus percentage chromium, sorry, copper, cracking tendency to cracking percent as a function of percentage magnesium, and cracking tendency as a function of magnesium silicides. So you could see if your consumable in your welding filler metal, if you use a silicon with 4 percentage, you see the cracking tendencies increase when there is a less silicon is present up to 2. But when the silicon is present more than 2, the graph slopes, the peak slopes back and it's becoming continuous, so you have less cracking susceptibility. So you should use a filler metal with having a more than 2 percentage, practically 4 percentage silicon. Likewise, use a magnesium with more than 6 percentage. So Al5Ci, Al5 magnesium fillers are used. They can be used for welding of aluminum alloys. So I think I have maintained the time given slot to me. These are the references I recommend you for detailed study. So for ASM handbooks, American Society of Metals handbooks, and some for various materials and their property. Just click on the www.azoom.com, and you also have a on the ASM Metals Handbooks and Design Engineers and American Petroleum Institute this and this particular AWS Handbook Volume 1. So this will give you, my presentation is prepared from these references and literatures available with me, and I thank you very much you all for your patience-full hearing to me. And I'm also author of a technical blog, and www.weldingknowledge.co.in. It's my technical blog, and on this technical blog, I just I take up questions from the engineering students, from the welding professional, from the welding people, and I try to provide technical guidance, suggestions, and recommendations regarding to welding metallurgy, filler metal selection, and you can subscribe to this my uh, blog. And I am also having a YouTube channel known as Welding Knowledge, and sorry, Welding Education. So with Welding Education, the URL of this YouTube channel, Welding Education, is also given in this weldingknowledge.co.in technical blog, and you can also subscribe my YouTube channel for uh, many talks, lecture series on the weldability issues, and all that. So, any questions from you people? I'll be very happy to give answer to your question. Now I am going back to my original screen, and I am now stopping screen sharing presentation. And hope you found this my talk interesting. But I want to know some just that's right. હેલો હેલો હા અત્યારે આપ કોણ બોલો છો? ઓકે ઓકે મેડમ, તમે 3-4 વાર ટ્રાય કરતા હતા. હું તમને થોડીક વારમાં કોલ બેક કરું, અત્યારે થોડીક એક ક્લાસમાં છો ને, હું કોલ ઓકે ના ના હું તમને તમે 15 મિનિટ પછી કોલ કરજો ને. થેન્ક યુ. ઓકે. Okay, sorry, I did some call. Okay, hope I'm audible again, and hope you found my presentation important and useful to you. And may I know the questions from the audience or the students or faculty members, please? Hello. I think over to Professor. Yes, sir. So I hope students have heard me and attended the talk. So any questions from your side? Hello. Can some student confirm me whether I am audible or whether my voice is reaching to you? Hello. I can see Jayesh Mahant, sir. Hello. 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 Mahant, sir. Sorry, you are not audible. I cannot hear you. Hello. Am I audible, sir? Okay, yes. Okay. Hello. Yes, Mahant, sir.
Hello.
Hello. Yes. Yes, I can hear
Am I
you.
audible,
Yes,
sir?
yes. Yes, yes, you are audible, sir. You're audible.
Hello.
Hello. Yes, sir. You are audible,
Okay,
sir.
okay. Yes, 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 sir.
Yes. Okay,
Sir.
okay. Sir, yes, sir. Sir, may I know you are your real brother of Professor Devang Mahant?
Yeah, yes, sir.
Yes, yes, yes. Okay, okay. I recognize you. We are colleagues. Actually,
Yeah.
we are colleagues and we are very good friends. I am from the same department, same
Okay.
institute, GC Gandhinagar, and
Okay.
your face very much resembling your yes, you both
Yes.
brother. Yes, so I could recognize you.
Yeah,
Okay,
right.
yes. So you are with Parliament University. Okay.
Yes, sir. I'm in
And
automobile engineering
October,
department, sir.
great, great to know.
Yes,
Good to
sir.
know from you.
Yes, sir.
You both are
I'm
in academics. You're doing well in academics. Good, good.
thank you very much,
So,
sir.
so,
I try to
so
your YouTube channel and subscribe maximum student and they
sure,
take benefits of your YouTube channel and
sure,
they maximum give the questions. Okay, sir. So
sure. Thank you.
thank you, sir. Thank you for giving such a good knowledge on metals and
Thank
their
you.
welding behaviors. Okay, and this
Fine.
is really helpful for our automobile students. Okay, sir.
Definitely.
So thank you very much for spending your good time, sir.
Great, great.
Okay.
Yes,
Okay.
it's my pleasure, and it's my pleasure altogether. And lastly, I would like to thank management of Power Institutions, your head of department, Professor Shailesh Parmar sir, Professor
Yes.
yes sir, and you, Professor Jayesh Mahant sir, for giving the opportunity to me to interact with the students of automobile engineering department.
Thank you, sir.
So I thank you all for considering me for this topic subject concern. And
Yes, sir. Yes,
in
sir. This is
future,
very
I'll be
helpful for
more
us.
than happy to. Yes, I'll be more than happy to interact with you in the future. Also, yes, yes.
Thank you, yes, sir.
Yes. So my
Thank you. Have
regards
a
to you.
good day, sir.
Yes,
Yes.
yes, sir. Same to you. Bye. Take care. Bye.
Bye, sir. Bye.
Should I leave? Okay, it's fine.
Yes, sir.
Thank you.
Yes, sir. You can leave, sir. Yeah.
Yes, sir. Okay. You can. Sir. Thank you. Thank you.